In example 4, the polynomial function that we are going to draw a rough sketch of is f of x is equal to 4 times the quantity x squared plus 1 times the quantity x minus 2 all cubed. Okay, we are going to follow the same process that we did in example 3. So the first thing we're going to try to do is identify the degree and leading coefficient of this function. So remember, don't waste your time. It's a lot of work to multiply this thing out. I showed you a shortcut in example 3. So the first thing you need to do, because we're after the leading term, you need to break this thing down. Okay, this is 4 times, then we've got the parentheses with the x squared plus 1. The quantity in parentheses is raised to the first power, so you can't break this thing down any further. But the x minus 2 is cubed, so that means you're taking the x minus 2 and you're multiplying it by itself 3 times. So we can write that part as x minus 2 times x minus 2 times x minus 2. Okay, so that is the first step, is breaking this thing down so you can clearly see all the factors written out. And now I'm going to highlight everything that I see with an x in yellow. So in this first set of parentheses, I see an x squared. And then the next set of parentheses, I see an x, and then an x, and then an x. And then you also need to look out front for any numbers. There is a number out front, and so I'm going to highlight that as well. So what we're going to do is multiply all these things that I've highlighted together, and that's going to give us the leading term. Okay, so the leading term, and that just means if you were to multiply all this stuff out, this would be the term containing the highest power of x. Okay, it's going to be 4 times x squared times x times x times x. So it's going to be 4 times x raised to, remember, since you're multiplying all these x's, you're basically adding the exponent. So it's going to be 2, 3, 4, 5, x to the 5th. Okay, the leading term is 4 times x to the 5th power. So that means we have a degree 5 polynomial. That's the highest power of x, and the leading coefficient is positive 4. So in this situation, we have an odd degree again, and we have a positive leading coefficient. Okay, so we can determine from this information, we can determine the end behavior. Okay, so if you go back to page 4, we need to find odd degree, positive leading coefficient. Okay, that's going to be this situation right here. So we're going to see that this function that we're dealing with is going to behave like x cubed. It's going to fall to the left and rise to the right. Okay, so basically I'll write out here, this function is going to behave like x cubed. Okay, and we know x cubed looks like this. Okay, so this polynomial that we're going to be drawing should be falling to the left. It should be rising to the right. So make sure you have that when you draw your graph in part F. Okay, in terms of writing this down all mathy, remember we have to make two statements about the end behavior. So first, what happens as your x values approach negative infinity? So if your x values get more and more negative in this direction, their y values are getting more and more negative. So their y values are approaching negative infinity. And then on the flip side, if your x values are approaching positive infinity, so if your x values are going this way, their y values are getting more and more positive. Okay, so this is another way, the mathy way of writing falls left, rises right. It is as x approaches negative infinity, the y values approach negative infinity as well. And as the x values approach positive infinity, the y values approach positive infinity. Okay, so again, when you draw your graph in part F, you better have something that falls left, rises right. All right, on to part C, the zeros, the x-intercepts. Okay, again, we're sticking to real zeros at this point. Okay, it is possible to get something imaginary, but we're going to only be listing the real zeros because those are the ones that physically appear on the graph. Okay, all right, so remember, to find zeros, okay, those are x-intercepts. So to find your zeros or your x-intercepts, the rule has been from section 2.1 that you need to set your y value equal to 0 and solve for x. Okay, so remember f of x is the same thing as y. So we need to say 0 equals our function. So I'm just going to use the one that's all factored out. So the 4 times the x squared plus 1 times the x minus 2 times the x minus 2 times the x minus 2. Okay, we need to take each factor and set it to 0. Factors are the things that we're multiplying together here. So I'm underlining each factor in red. Okay, so the first thing I'm going to do is set 4 equal to 0. Okay, so if I come down here for the work, okay, I'm going to set 4 equal to 0. Okay, this doesn't make any sense. Okay, remember I told you in the last example, it never makes sense to set some non-zero number equal to 0, so you can kind of ignore that part. You can only set the factors that contain a 0, or sorry, only take the factors that contain an x and set those equal to 0. Okay, so if I go back and I look at my next factor, the next factor I have is the quantity x squared plus 1. Okay, I'm going to set that equal to 0 and solve. So I've got x squared plus 1 is equal to 0. So I'm going to move the 1 over by subtracting. I'm going to get x squared is equal to negative 1. I've got something squared is equal to a number. So to undo the square, I'm going to take the square root of both sides, put a plus or minus out front. That's something we learned early on. Okay, so the square and the square root cancel, and I'm going to get x is equal to plus or minus the square root of negative 1. This is bad, 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 bad. Okay, this is an imaginary number. Okay, this is not a real 0. I don't know if you know this or not. I'll write it over here. I'll put it in a different color so it stands out. Like I said, we're about to get into imaginary numbers. The square root of negative 1 is defined as I. Okay, that's the basic imaginary unit. Okay, so you have two imaginary zeros here. Okay, you've got the plus or minus out front, and then the square root of negative 1 is I. So positive I is an imaginary 0, and then negative I is an imaginary 0. Okay, and we're not going to put these in our table because we're only asked for real zeros. Okay, these are imaginary zeros. Okay, they don't physically show up on the graph. Okay, all right. So then if we go back up to our factorization, I've got x minus 2, and I've got it written 3 times in the factorization. Okay, so I'm going to take x minus 2, set it to 0, x minus 2, set it to 0, x minus 2, set it to 0. Every time you solve this, you're going to get x equals 2. This is a real 0. So you get one real 0 that will physically show up on the graph, and that's going to be at x equals 2. Okay, because we got it once, twice, 3 times, its multiplicity is 3. Since that is an odd number, the odd multiplicity, the rule is the polynomial function will cross at this x-intercept. Okay, that's it. That's all that goes in this table. Okay, you're going to have one physical x-intercept or 0 on the graph itself. Okay, and the graph will be crossing there. Okay. All right, so let's get another point. That's going to be the y-intercept in part D. So we need to go back to the original function. We need to set x equal to 0 and solve for y. So if we go back up here, we're going to get 4 times 0 squared plus 1 times 0 minus 2 times 0 minus 2 times 0 minus 2. This is going to give us 4 times 1 times negative 2 times negative 2 times negative 2. All right, so if we multiply all these numbers together, 4 times 1 is 4 times negative 2 is negative 8 times negative 2 is 16 times negative 2 is negative 32. Okay, so the y-intercept here is going to be the ordered pair x is 0, y is negative 32, so that's way down there. Okay, like I said, with these higher degree polynomials, you can really get some big y values. Okay, all right. So moving on to part E, and then we'll put everything together. What's going to be the maximum number of turning points that you can have on this graph? That's going to be the degree minus 1. We found that the degree is 5, so this is going to be 5 minus 1. You can have at most 4 turning points on the graph. Okay? All right, it is time to put all of this information on the graph. Okay, first thing we've got to do is scale the X and Y axes. Okay, I'm leaving that up to you. You have to put a scale on here so I can see where you're putting points. Okay, we only have one x-intercept, so it's at 2, so it's fine and dandy to just keep the x-axis, put tick marks every 1 unit. Okay, so like this. And then as far as the y-axis goes, I'm going to take a look at the y-intercept. It's huge. It's at negative 32. So I think I'm going to go by 4s. So this is negative 4, negative 8, negative 12, negative 16, negative 20, negative 24, negative 28, and I'm going to be off the grid a little bit. We'll say this is negative 32. Okay. All right. So, if you went in the positive direction, it would be the same, just positive 4, 8, 12, and so on. Okay. So now I need to put some points that I know are on the graph. Okay. We know we have an x-intercept at x equals 2. And we also have a y-intercept at 0, negative 32. That's going to be right here. So your polynomial function is going to have to go through these 2 points. Okay. All right. So let's see here. We're going to have to go ahead. We can basically go ahead and connect the dots. Remember, this is the only place that you're going to intersect the x-axis. At x equals 2, you should be crossing. So it looks like, since there's a point down here, it looks like you're going to be coming from below the x-axis to above. Okay. And then you need to incorporate the correct end behavior. Okay. We need to be looking like x cubed, so we need to be falling left, rising right. Okay. So let's try to draw this in. All right. So I'm going to start at the y-intercept. I'm going to come up. Let's see if I can pull this off. I'm going to come up and cross at x equals 2, and then so I'm basically falling to the left, and then I just need to rise to the right. Okay, that's it. It cannot come back down because then you will have another x-intercept, so that's not possible. Okay, so this is kind of a very boring graph. Okay, this is what it looks like. Okay. Let's go through and make sure we've met all the attributes. Okay, you can even put this in a calculator and you'll see this is exactly what it's going to look like. Okay, so the first thing we need to check in our picture, are we falling left and rising right? Okay, so if we come down here, if you follow where my cursor is, we are doing that. We are falling left, we are rising right, so that looks good. And then next, do we have an x-intercept at 2? And is it crossing there? Okay, yes, here it is. You're crossing the x-axis at 2. You're going from below to above the x-axis, so that looks good. And that's your only x-intercept. You have a y-intercept at 0, negative 32. And then do we have no more than 4 turning points? Okay, well, let's look at this. Okay, that's associated with increasing, decreasing. So trace the curve from left to right. Okay, so follow my cursor. If I'm going from left to right, we're increasing the whole time. So there are no turning points. Is that okay? Okay, yes, because what the rule is saying, you can have at most 4 turning points. So you can have 4 turning points, 3 turning points, 2 turning points, 1 turning point, or 0 turning points. We happen to have no turning points here. Okay, so this is exactly what the graph looks like. It's a rough sketch, like we only have a couple of specific points on there, but this is basically what it looks like. Okay, if you were to go to your calculator and plug in this function, you should see basically this picture.